Hi there, this is Matt Heffernan. Welcome back to my channel. This is the third episode in a series that seeks to demystify programming in assembly language for the 6502 family of 8-bit processors. We're using the Commander X16 as a target as it has a 65C02 and is a particularly excellent platform for this learning process. If you haven't seen the previous episodes and need to start at the very beginning, please go back to my channel and don't forget to subscribe and click the bell for notifications while you're there so that you know when the next episodes come out. And start this playlist from the beginning. As a recap, in the first episode, we went over the basics of assembly development, what some of the terminology we are using means, and going through how the different tools work. In the second episode, we went over all the different addressing modes and showed how assembly instructions can access data in different ways. In this episode, we are going to show how programs can run not just as a straight line of instructions, but as a variable path. We already saw how jumping worked, but now we are going to learn about conditional branching and subroutines that return back to where they were called from. After this lesson, you may be able to create a program that could actually be useful. Up front, let's take a look at a case study of how flow control is handled with C as compared to assembly. I'll have some similar examples later in this episode, and for all of them, the syntax used in C is very similar to that of many high-level languages, so it should be easy to follow even if you aren't a seasoned C programmer. Now, in C, like with most languages, you have some basic constructs that are used for flow control, like if statements, while and for loops, and switch statements. In 6502 assembly, each instruction does basically a single thing, so you have to use branching instructions like BEQ, BMI, and others that change the path of execution based on bits in the status register. Here we see a very simple if-else statement in C that will increment a value if it is equal to 5. Otherwise, it will decrement it, then return from the current function. On the assembly side, we don't have anything like an if instruction, so we need to do the comparison in a couple steps. First, we need to load the value into the accumulator. Then we can compare it to 5. Now, if the value is equal to 5, the CMP instruction will result in the Z bit getting set, meaning that the program will take the BEQ branch to the incval label. If the Z bit was not set, meaning that the value was not equal to 5, then execution would have continued on to the DEC instruction, which will decrement the value, and then the BRA instruction does an unconditional branch to the done label. An unconditional branch behaves just like a JMP instruction, but it uses relative addressing, so it can only be used for nearby addresses, but has the advantage of taking up less space. Please note that BRA was added to the instruction set for the 65C02 and is not available for earlier processors. Going back to the BEQ branch, if it was taken, the INC statement after the incval label will be executed next, skipping over the DEC and BRA instructions, and the value will be incremented. Then it just continues on to the RTS after the done label. So that's it, 2 pieces of code that do the exact same thing. In fact, there's a good chance that a C compiler would compile that C code snippet into that very same set of machine code instructions specified by the assembly. But we have glossed over quite a bit already, so let's go do some more in-depth review. In the last episode, we touched briefly on relative addressing, and how it uses a signed 8-bit value instead of an absolute 16-bit address. That signed value must be added to the next program counter address to get the target address. Thankfully, most assemblers will automatically convert simple labels to relative offsets for you, but it will check to make sure that you aren't trying to branch too far away. As the offset is signed 8-bit, the range is only -128 to +127, so the address of the instruction following the branch needs to be within that range of its target. If it's not, the assembler will fail and give you an error message stating that the label is not within the valid range. If you are doing an unconditional branch, this is easy. Just change the BRA to a JMP and you are all set. However, for conditional branching, it means you may need to invert your branching conditions and use jumps to get to those distant addresses. In the first example here, we see a perfectly valid set of branches that will assemble into code that works as expected. Here we have placed a BEQ instruction at hex 107E that targets a label at hex 1000. That requires a relative jump backwards from the address of the next instruction by 128 bytes, which is the maximum allowed. Then there is the BRA instruction that will be placed at hex 1080, then targets a label at hex 1101. That is only 127 bytes further than the next instruction, which is the maximum in that direction. If either of those labels were even a single byte farther away, this code would not assemble, which we can see in the middle example. Now, we have shifted the code so that the BEQ wants to go back 129 bytes, and the BRA wants to go forward 128 bytes. Neither instruction is valid, and an assembler like CA65 will fail with errors for both lines. In the example to the right, we fix that code by doing a shorter hop with that BEQ statement to some new code that does an absolute jump back to hex 1000. If we don't take that branch, then we replace the earlier BRA with another jump, which is an easy fix as the instructions do the same thing with different addressing modes. You could have replaced the BRA in the first example with a jump too, but that would have made the code a byte larger, and sometimes every byte counts. In the first episode, we talked briefly about the status register, also known by the letter P for processor status. 7 of the 8 bits in this register are used to provide insight into the results of the most recently executed instructions. In this table, you can see the mapping of these bits to their meaning and which branch instructions use them. As you can see, only the top 2 bits, N and V, and the bottom 2 bits, Z and C, are used for branching. The N bit is set when the result of the last operation is negative. That is, the high bit was set, so it would be negative if interpreted as a signed 8-bit value. You can use the N bit with the BMI and BPL instructions. BMI stands for branch if minus, meaning the N bit is set. BPL stands for branch if plus, meaning the N bit is clear. The V bit is set in an overflow condition, meaning that a math operation resulted in a different sign from both operands. For this, you have BVS for branch if V set and BVC for branch if V clear. The overflow condition is both rare and usually irrelevant, so these instructions are not often used for the 65C02. But for processors that don't support unconditional branching, you can usually safely replace a BRA instruction with a BVC instruction, as in most cases you can depend on the V bit being clear. The Z bit is set when the result is 0, which is the case when you compare the contents of a register with its exact value. So the BEQ instruction stands for branch if equal, meaning the Z bit is set. If the Z bit is clear, you can branch with a BNE, or branch if not equal instruction. The C bit is set when a math operation results in a carry. This is used for doing math with 16-bit or wider values, where you may have to do a carry, just like doing addition by hand. The carry bit is also used for a few other things, so it can be handy to use a BCS for branch if carry set, or BCC for branch if carry clear. Those 3 other bits in the middle of the status register are used for important things, but we'll get into those in a later episode. We've already seen the CMP, or compare accumulator, instruction used earlier to set up the use of a BEQ instruction. But compare instructions work for the index registers too, with CPX and CPY, and can be used not just for testing for equality. You can also use a combination of the N and C bits along with the Z bit to determine relationships between the register and the operand of the compare. This is because the compare actually does a subtraction, which is why an equal result sets the Z bit. Anything minus itself is 0. This table shows you how the 3 bits are set after the 3 types of compare outcomes. First, if the register value is greater than the operand value, then the C bit is set, as subtracting the operand value means that no inverse carry is required. I know this seems a bit weird, but generally, having the carry bit set is the default state for subtraction. But as the values are not equal, the Z bit is clear, as is the N bit, as the subtraction result would be positive. If the values are equal, then both the Z and C bits are set. So a BCS after a compare means that a branch will occur when the compare operand is less than or equal to the register value. If the register value is less than the operand value, then the N bit will be set while Z and C are clear. This means that a BMI will result in a branch, but so will a BCC, as we can see that the N and C bits are always the opposite state after a compare. So BPL and BCS are also interchangeable after a compare. So compare instructions are used for a lot of branching, but the effects of the other instructions are important or even necessary to get certain states to happen. Some of the status bits can be just set directly, and in the case of those used for branching, you can do a CLC to clear C, an SEC to set C, or a CLV to clear V. The other bits can only be set using the stack to pull a value into the whole status register at once. We can use the PLP instruction to pull the value on the top of the stack into P, also known as the status register. You can even set that one unused bit if that's important to you, but generally we are depending on the side effects of math and load operations to set these bits. Here we have a sample program that uses each of these methods. This isn't part of the example program for this lesson, but just an illustration that shows you the values in the accumulator, the top of the stack, and the 4 status bits we care about for branching. First, we load the value we want to load into the status register into the accumulator. Hex C1 means that the N, V, and C bits will all be set and the rest clear. To get that in there, first we need to push this value onto the stack with a PHA, or push A instruction. Then we can do a PLP to pull it into P and set those status bits, so now all 4 have a known value. Now we can see that the CLC and CLV instructions will clear the C and V bits respectively, leaving only the N bit set. Loading 0 into A will result in clearing that N bit finally, and now setting the Z bit as the result of the load is in fact 0. After that, we will do the highest addition we can do without changing the sign, with an ADC of 127. This means add with carry, so as the C bit is clear going in, we will just be adding 127 to 0, resulting in 127. This clears the Z bit, but nothing else gets set, as the result is still positive and no overflow has occurred, and no carry would be applicable to a subsequent addition. Adding 1 to A now will result in both a negative result and an overflow. The unsigned decimal value in the accumulator will only be 128, but as that is hex 80, the signed bit is set, meaning the signed decimal value would be minus 128. Adding 127 again will clear that overflow bit, as now we are adding a positive value to a negative one, so overflow no longer applies. This brings the value in A up to hex FF, which could be interpreted in decimal as -1 or 255. Adding 1 once more will zero out the accumulator, which sets the Z bit again, but this time the carry bit is also set, as this was from an addition instead of a load. We would want to carry that one into another operation. Now that we've seen all the ways the branching conditions can be set, let's take a look at another case study. A very common operation is to copy data from one part of memory to another. In C, we could do this with a simple for loop that uses an index variable that is used to iterate across both the source and destination arrays, doing an assignment for each element. Here we are copying the first 4 bytes from the bar array into the beginning of the foo array. This can also be done very easily with assembly, and with minimal memory access thanks to the X index register and an indexed addressing mode. First, we need to initialize X with the value of 0. Then we have a label to show where we want to branch back for the next iteration. We don't want to reinitialize X, as we'll be using that to index into our data. We load a byte from bar using X as an index, then store it to foo with the same value of X as an index. Then we increment X and compare it to 4. If it's not yet equal to 4, we branch back to the loop point and do it again. Once X is incremented all the way to 4, we know that the first 4 bytes have been copied, and we can fall out of the loop and continue our program. So we were able to do the same work as the C code without having to allocate any space for I for the sake of this loop or do any sort of address math in our code. The processor is taking care of all that for us, so this code will be very small and fast. Now let's change gears and take a look at a totally different case study. In C, we can define functions by having a return value type and an identifier, followed by an argument list in parentheses and a code block in braces. Here's the simplest type of function you can have in C, with a void return type, meaning it returns nothing, and no arguments, so just an empty pair of parentheses. Then, in the code block, we simply increment some variable, and then implicitly return from the function by closing the code block with the right brace. Then we can call that function by just putting the identifier in another part of the program, followed by parentheses and a semicolon. A lot of this type of syntax is not possible with assembly, so it has to be done differently. A subroutine can start at any address in your code, and usually that starts with a label. Then the path of execution needs to end with an RTS instruction to return from that subroutine. We recreate that simple C function by doing a simple inc instruction after the label, and then ending with RTS. If you have branching in a subroutine, you need to make sure that all possible paths will end with an RTS, or your subroutine will never return. Then to call the subroutine, we just use the JSR instruction to jump to that subroutine using its beginning label. After that subroutine returns, the program counter will return to the next instruction after the JSR. This is because that address is placed on the stack before changing the program counter to the address specified in the operand. JSR only uses the absolute addressing mode, so you can't do indirect addressing like a straight jump. In this lesson, we won't be writing our own subroutine, other than the main program itself, but we will be making use of a subroutine available to us without having to include it in our program. That is because it is in the ROM as part of the Commander X16 kernel, which was based on the original Commodore kernel used in their most popular 8-bit computers, including the best-selling Commodore 64. So we can make use of most of those subroutines that were defined in that legacy kernel, providing a fair amount of compatibility with some low-level operations like file and keyboard access. These subroutines don't use the stack for arguments and return values, as some high-level languages would, but a combination of registers and specific zero-page addresses. One of the legacy subroutines carried over is char out at the hex address ffd2, which works much like the putC function in the standard C I/O library. With putC, you specify a character value and a file to write it to. If we specify the standard output file, it will print that character to the console screen. With char out, the console is the default destination, so whatever value is in the accumulator will be printed out. In both cases, we use the value hex 35, which is the 5 character. As in both ASCII and PETSCII, numerical characters start with 0 at hex 30 and go up to 9 at hex 39. So both programs should result in 5 being printed to the screen, and that's it. The nice thing is that since the lion's share of the code in this snippet is being executed out of ROM, the program loaded into RAM is extremely small. If we were to use the C example, we would need to link in the big C library to support that one function call, taking up valuable space. If you watch my video called Hello CC65, you can see exactly how expensive that can be. So let's get to the example program for this lesson. We want to apply the concepts we learned to do some simple data processing. We're going to go ahead and reuse the data array from the last episode, but first we need to set a couple of constants. As we saw earlier, we are going to define the address for the char out subroutine in the kernel ROM so that we can print out our results to the screen instead of having to use the debugger or manually peeking at an address. We're going to make this even easier by defining the new line character, which is hex 0D in PETSCII. It works the same as the ASCII carriage return at hex OA that you may be familiar with. This is going to let us print results on separate lines, as we will soon see. We're going to start the program with a loop to iterate through the data array and compare each value to hex 55. If the value is less than that, the loop will continue to the next index by doing a BMI after the CMP instruction. If the value is greater than or equal to hex 55, the branch won't be taken and the index will be printed out. We do this by first transferring the index from X to A with a TXA. Then we change that index into a PETSCII character by adding hex 30 to it, as we have seen before. But this time, instead of doing an addition, we use the ORA instruction. This does a bitwise OR of the value in the accumulator with the operand value. If we used the ADC instruction, we would have had to make sure we cleared the carry bit ahead of time, which makes the code longer and slower. In this case, we know that the index will be between 0 and 7, so we're guaranteed that the OR will work in all cases. We'll look at bit operations more in a later episode, but this is something that will come in handy every time you are printing decimal digits. At the next n label, we know that we are done with the current index, as we have either printed it or skipped right to this point after the BMI. Now we can increment the index and compare it to 8. If it's not 8 yet, the BNE will take us back to the beginning of the loop to process this new index. Otherwise, it is 8 now, so it's time to print out that new line to make sure that only the results from this loop are on the first line of output and we can move on to the next part. The last loop used the n bit to determine which indexes would be printed out. In the second loop, we copied the same code, but changed the parts in red to try branching based on the carry bit. So instead of just doing a comparison, we're going to add hex 55 to each value in the array and print out the indexes of the values that don't result in the carry bit being set. That means that the sum of the value and hex 55 is less than hex 100. Otherwise, if the sum is larger, the carry bit will be set, and the BCS instruction will skip over printing the index. So aside from that, all that needs to be changed here are the labels, and this loop is done. The third and final loop of this example is very similar to the last one, with only changing the BCS to a BVS and some new labels. The addition will result in an overflow condition if the data value is positive, And the result of the add C is negative, as we are adding another positive value in hex 55. The negative values in the array won't cause an overflow, as we have operands with mixed signs, so the signs of the result won't matter. After one last new line, we return back to the basic prompt with an RTS, and our program is complete. Now let's go look at it in our text editor. Once again, we see that same boilerplate at the top of the code to get it to start hex 80D. Then we have the data declaration and the 3 loops, 1, 2, 3, and we're done. We can build this with another build script, just like last time. Now the assembly code file is called branch.asm, and we're going to generate a binary called branch.prg in all caps. So let's go ahead and build this. We'll run the build script, and we can see that branch.prg is there. Now we're ready to run it in the emulator. We'll go ahead and make that bigger. There we go. Okay, let's load branch.prg and run it. As expected, we see 3 lines of numbers printed out, so let's take a closer look. On the first line, we see 3, 4, 5, 6, which means that those 4 indexes in the data array have values that are greater than or equal to hex 55. That would make sense, but why is index 7 not there? That value is hex EF, which would seem higher. Well, remember that this determination is done with a subtraction. When you subtract hex EF from hex 55, you get hex 66. So the result actually wraps around to being positive again, just like when you subtract the first 3 values. It's a little counterintuitive, but these are considerations you need to make when deciding which branch instructions to use. If you know what the expected range of values are when you write your program, it makes it much easier. On the second line, we see 0, 1, 2, 3, 4. This makes much more sense, as we know that adding hex 55 to those first 5 values won't result in a carry, as the sums are all under hex 100. The remaining indexes do result in carry as expected, so they aren't printed out. On the third line, we see 0, 1, 4, 5, 6, 7, which means that indexes 2 and 3 cause an overflow. This seems like a slightly random section of the data array, but it does make sense when you understand the causes of overflow. Remember, overflow only happens when both operands are the same sign, and the result is different. For each index, we are adding hex 55, which is a positive value. So right off, we don't expect overflow when adding it to any of the negative values, which is why 4 through 7 didn't result in overflow. With the first 2 values, the indexes 0 and 1, adding them to hex 55 will result in positive numbers, so no overflow there. But indexes 2 and 3 have positive values high enough that when added to hex 55, result in values over hex 7f, or decimal 127, which is an overflow. If you are interpreting the result as unsigned, then overflow is meaningless, but the processor doesn't know or care about your interpretation. The V-bit will be set, and you can use that or ignore it. So that's it for our lesson on branching and subroutines. Not too bad, right? There are some weird ways that these status bits work, but for the most part, it is pretty straightforward and very powerful. With some careful planning, you can set up these branches in ways that require very little code by taking advantage of a bit of foreknowledge and some convenient side effects. We're going to be doing a lot of branching and creating subroutines in future lessons, so we'll get some of the strategies later on. But for now, you have the basic concepts, and we can get right to our next lesson. Until then, I hope you have found this series helpful so far, and that you subscribe to my channel and click that bell for notifications so you'll find out right away when the next episode is posted. If you have any questions or suggestions for future episodes, please feel free to leave them in the comments, but don't forget to check out the GitHub repo linked in the description. There you will find all the materials for these lessons, including today's episode, which is in the Lesson 3 subdirectory. All of this code is 100% free and open source, so please feel free to use it however you see fit. Thanks, and I'll talk to you again soon. Bye-bye.